Okay, thank you for the introduction and having me here. So I'd like to talk about the contact topology of the real projective space. So let me first start with some basic things. So the fundamental principle in contact topology is a dichotomy between over-twisted and tight, discovered by L. in dimension 3 and Bowman, L. Murphy in dimension higher than 3. Okay, so the over-twisted contact structure are those kind of purely classified by the underlying topological data, and it can be in some sense understood as a simplest contact structure. And tight contact structure are those which are not over-twisted, so they contain some information other than the topological information. And we know that over-twisted contact structure is not fillable, so we can categorize tight contact structure briefly using their fillability. So one way is using this Weinstein fillable, exactly fillable, strongly fillable, and weakly fillable, and then tight. Okay, so I'm sure the definition of filling is familiar to most of you, but I want to quickly recap the definition. So given contact manifold YC, a symplectic manifold with that boundary is called a strong filling if there is a pointing out Liouville vector field near the boundary, so that the lead derivative of the symplectic form itself and the interior product of vector field of symplectic form restrict to the boundary is a contact form for the contact structure. And it's called exact filling if this vector field is defined everywhere on the filling. So in particular, the symplectic form will be an exact form. And a Weinstein filling is you require something more on the vector field, that if you assume the vector field is gradient-like. Okay, and from this definition, it's clear that we have this fillability is inclusion, but it's a natural question to understand whether these are proper inclusions or there are actually a difference between these different kind of fillabilities. And this question was answered affirmatively for many cases. So for the exactly fillable but not Weinstein fillable, the example was found by Bourdain in dimension 3 and Bourdain-Crowley Stipchitz in dimension higher than 5. And strongly fillable but not exactly fillable example was first found by Gigini in dimension 3. And weakly fillable but not strongly fillable are first found by L. in dimension 3 and Bourdain, Gironella, Marino in dimension higher than 5. And tight, not weakly fillable are first found by Antony Honda in dimension 3 and Massot, Niederkruger, Wendell in dimension higher than 5. And so we see from here, there's a difference between dimension 3 and higher dimensions, both in like method and examples. And the only missing piece here is kind of the strongly fillable but not exactly fillable in dimension bigger or equal to 5. And the good news about this question is we kind of have a very nice guiding example, which is RP2n-1 with a standard contact structure. And the standard contact structure is coming from the Z2 quotient of the standard contact structure on sphere. And it is a conjecture of L. that saying that this real projective space with a standard contact structure is not exactly fillable if only if n is bigger or equal to 3. So if this conjecture is true, then we have examples in all higher dimensions. And some remarks about this conjecture. First of all, RP2n-1 with a standard contact structure is not Weinstein fillable, if only if n is bigger or equal to 3. And this is something relatively easy to see because if you have a Weinstein filling, then it kind of can be built from handle bodies of index at most half of the dimension. So it will put a very strong topological constraint on the boundary. And this statement can be proven using just topological method. And in fact, the topological obstruction for Weinstein fillability is completely understood nowadays by the work of Bourdain, Crowley, and Stipchitz. The other thing is RP3, when n is 2, RP3 with a standard contact structure actually has the exact filling, which is a cotangent bundle of a sphere, which is actually also a Weinstein filling. And for all these RP2n-1, we also have a strong filling filling, which is the total space of the degree -2 line bundle over CP n-1. And this can be viewed as a resolution to the Z2 quotient singularity. And the link of this singularity is exactly the contact RP2n-1. And in the case of n equals to 2, we actually kind of have two fillings of RP3. One is exact, one is not, but the underlying manifold are diffeomorphic. Okay, so we need to if we try to give a solution to this conjecture, we need to understand what happens in the n equals to 2 case and what went wrong when we have a strong filling. Okay, so the main result I want to talk about is a solution to the conjecture in many cases. So RP2n-1 is not exactly fillable if n is not power of 2, which in particular implies n is bigger or equal to 3. This result also holds for that this RP2n-1 is not has no symplectically a spherical filling, and there's no Calabi-Yau filling. By Calabi-Yau, I mean the first string class is a torsion. And the n equal to 3 case of this theorem is also proven by Gijini and Niederkruger using a different method. And our method works for other quotient singularities like is a sphere quotient by ZK. Here, ZK is acting by the case root of unit acting on the diagonal of Cn. But the actual statement of non-fillability will have some specific condition on n and k. But combine them, we get an answer to the proper inclusion question, which is in dimension higher than 5, there exists strongly fillable but not exactly fillable contact manifolds. The remaining case, which is n equals to a power of 2, is provided by the next simplest quotient singularity, which is quotient by C3. Okay. The proof actually has basically 2 steps. One is a symplectic step, one is a topological step. The symplectic step only uses the condition that n is bigger or equal to 3, which is the condition in the original conjecture. And n equals to 2k condition is only use the topological proposition, but I don't know how to get rid of it. Okay, so the symplectic proposition step is the following, that we can show for n is bigger or equal to 3, if we have an exact filling, then the following will be true. If n is odd, then the real coefficient cohomology is just rank 1 in degree 0. And when n is even, the real coefficient cohomology is either rank 1 or rank 2. In the latter case, the cohomology is supported in degree 0 and n. Okay, so the upshot is the cohomology is a filling. If it's exact, we have relatively small topology. And the topological input is the following, that if we have a strong filling, in fact, in an almost complex filling of the RP2n-1, and in here, I'm assuming n is not power 2, so I can write n as power 2 times some odd number bigger or equal to 3. And then we have these two map are surjective. So here, whenever I don't write out the coefficient, I mean the z coefficient. So I'm using, so in this case, z coefficient cohomology of RP2n-1 in this degree is z2. And I'm saying that these two maps are surjective. And this proof is really simple. We just try to compute the ith Chern class of the standard contact structure, because we know that if we have a symplectic filling W, then the ith Chern class of the filling restrict to the boundary is the ith Chern class of the standard contact structure. And as long as we show the kind of 2 to the case Chern class of the contact structure is non-trivial, then it's proven. So we basically only need to compute the Chern number. And for this, we can use a natural filling, which is the total space of degree -2 bundle, whose total Chern class is computed by 1 plus u to the n times 1 minus 2u. And we need to understand the map restricting to the boundary, but this is just a degree -2 circle bundle over CPM -1. So this restriction map is basically mod 2 map. So in this case, we can actually compute all the Chern classes of the contact structure and argue that these two relevant contact Chern class are non-zero. And when n is power 2, then it means actually the standard context structure has total Chern class is just 1. It's trivial. Okay. So now we have everything to prove the main theorem. So to prove the main theorem, first we note that from the symplectic proposition, if we have an exact filling, then we have all these 6 integral cohomology are torsion. And these are like centered around the surjective cohomology we mentioned in the topological proposition, this H2 to the k plus 1 and the symmetrical one. Okay, and the reason is the free rank is supported in either degree 0 or degree in the middle degree, which is very far away from these two. So they are all torsions. And then we can get the long exact sequence from the relative cohomology, which is around this interested degree. And the middle Z2 here is the cohomology of RP2n minus 1 in degree 2 to the k plus 1. And then we have a symmetrical one. Then what we can do is we can replace the relative cohomology by cohomology of the filling. And this can be done first using the Lefschetz duality. We pass the cohomology, relative cohomology to the homology of the filling. Then we can use the universal coefficient to relate the homology of the filling to the cohomology of the filling with a degree shift of 1. And this one, this second isomorphism is true because all these groups are torsion. So we know they are isomorphic groups. Okay. And we can replace all these relative cohomology and end up with these two long exact sequence. And then from the topological input, we know that this guy map here is surjective. So that means this group is iso here. Notice that these two groups are torsions. That means they are like finite abelian group of the same size. And from the second row, we know that this map is again surjective. So we know that the middle one is kind of twice the size of the first one. They are all torsion, but they are the same group as the previous isomorphic groups. So we get contradiction. It's so that proves the symplectic proposition. Okay. Any questions so far? All right. So the basic thing the important thing we need to prove is the symplectic proposition. So the idea for the proof is notice that this RP2 minus 1 has a double cover, which is a standard sphere. And this standard sphere has a very nice property that whenever n is bigger or equal to 2, for generic, and you choose the contact form, which is coming from kind of ellipsoid contact form, you perturb it a little bit. And in this case, for a general contact structure and for a point constraint, there is exactly one holomorphic curve, or one holomorphic curve passing through that point constraint at asymptotic to the shortest Reeve orbit. Okay, and this curve will completely contained inside the symplectization. Okay, and the last part is completely contained inside the symplectization is where I use the condition n is bigger or equal to 2. Okay, and the significance of this holomorphic curve is this curve actually kills a unit, which is represented by this point constraint. So the existence of this curve basically says the unit is a co-boundary in the symplectic cohomology. And if you kill the unit in a unital ring, you kill the whole symplectic group. What we claim is the same phenomena will hold for RP2n minus 1 as long as n is bigger or equal to 3. That is, we have the vanishing of symplectic cohomology for this imaginary exact filling. Okay, and then we can use the following property to get an estimate of the cohomology of the filling. So if I have 1 plus a is mapped to 0 in this continuation map from the cohomology of the filling to the symplectic cohomology of period filtered symplectic cohomology for some positive degree a, then I know the map from the positive filtered positive symplectic cohomology to the cohomology of filling is surjective. Okay, so for this proposition, the key factor is this 1 plus A is the unit in the ring structure of the cohomology of a filling. So this basically says a unit is mapped to 0 in this map. So that will carry the full symplectic cohomology. And in this case, the full positive symplectic cohomology will be isomorphic to the cohomology of filling. But I'm not going to use that as the full positive symplectic cohomology typically has infinitely many generators. So it's not a good thing to use to estimate the cohomology of the filling. So I'm using a filter version. And in that case, I only get a surjective map, which is not necessary. It's never isomorphism. Okay. And this is actually the proposition where I use exactness. So I forgot to mention that this proposition is true if W is exact or symplectically spherical, because if it's not a exact filling, say it's a strong filling, then the actual map here should be replaced by the continuation map is from the quantum cohomology to the symplectic cohomology. As a group, it's basically the same thing, but the ring structure will be different. So in particular, 1 plus A may not be a unit anymore in the quantum cohomology. In fact, it can be a 0 divisor. So the whole argument will break down. Okay, so this is where we use exactness. All right, so next I will move on to the actual setup of proving the theorem. So I will tell you the symplectic cohomology model I will use. So first I need to use a specific contact structure on the boundary. So this RP2n-1 has a very nice boosted 1 contact structure, which is kind of more spot contact structure. But I'm going to perturb it into a most non-degenerate contact structure. You can do this by choosing a perfect Morse function on the CP(n-1), and you pick this critical point Q0 to Qn-1, order them by the critical values, and the perturbed contact form will have the following property, that all these simple reorbit will be the S1 fiber over the critical point Qi, and the period of the reorbit will be ordered the same way as the critical value of F. And I ask all the periods smaller than 2 is basically all these simple reorbit or double cover of this simple reorbit. And among them, the key periodic orbit is this gamma 0 square. It's a double cover of the shortest simple reorbit, which is, if you lift this periodic orbit to the double cover, it's actually corresponding to the shortest reorbit on the ellipsoid contact form, which is exactly the reorbit having this holomorphic curve carries the unit. So this is actually our key player. Okay. And next, I'm going to tell you setup for the symplectic cohomology. So for this, I'm going to use an autonomous Hamiltonian. So I take my Hamiltonian to be 0 on the filling, and on the cylindrical end, it will only depend on the cylindrical coordinate r, with the property that the derivative is a for r is big enough. And then we pick a Morse function on Morse function g on the filling, with a unique minimum q, which will represent the unit 1 in the cohomology, and with the requirement that the radical derivative on the boundary is positive. And then we pick two generic points, gamma hat and gamma check, on the image of gamma bar. So this gamma bar here is the Hamiltonian orbit corresponding to the reorbit gamma. So because I'm choosing the autonomous Hamiltonian, so here, this Hamiltonian, non-constant Hamiltonian orbit will come in S1 family, and it corresponding to the reorbit. Okay. And then we can define the Floer-Cauchy complex by the critical point of G and gamma check and gamma hat for all these reorbits of periods smaller than A. And the differential is defined by counting the following cascades. So these cylinders are essentially solutions to Floer equation. And here it's also kind of cylinder, but near this point, because the condition is that the derivative g is bigger than 0. So this point is necessarily inside the filling where the Hamiltonian is 0. So around here, the equation is just a d-bar equation. And all these horizontal lines are a flow inside the image of the Hamiltonian orbit. And the convention is it's always flow towards a check orbit. So it's always towards check. Okay, and here is some flow following the gradient of my Morse function G. And this is exactly the cascade model constructed by Bourgeois and Wanshaw for autonomous Hamiltonians. All right. Okay. And from here, the critical points of G will generate a subcomplex, which is a cohomology of the filling, and this check hat orbit will generate quotient complex, which is just the positive cohomology. And then we have, in general, a Z2 graded line exact topological line exact sequence like this. Okay, and this map from the positive one to the cohomology of filling is defined by the +0, which is exactly by counting the second type of moduli spaces. And we want to show that a class like 1 plus A is mapped to 0 in the first map. So it's basically the same thing as saying that 1 plus A is in the map, in the image of SH plus into the cohomology of filling. We want to show this. And in other words, basically what we need to show is we want to find a positive cochain complex C, which is a closed form, a closed class, and the D+0C act on it pair with Q, which represents 1 unit here, is non-zero, right? If we prove this is true, then we can apply the proposition I mentioned before to show that the cohomology of the filling is controlled by the positive symplectic cohomology. Okay. And what we claim is actually this class C can be written as this gamma 0 square check plus some error correcting term for n is bigger or equal to 3. And that's kind of the claim. Okay, so the first let's compute what is D+0 D+0 gamma 0 square check pair with Q. The claim is it's actually 2. So the argument is basically using next stretching. Okay, so what we are interested in is some moduli space like this. The typical one will look like this because it's from a check orbit. So it's because all these flow lines flowing towards check. So there's this kind of reduced to a point constraint. And here you have point constraint Q. And you might have multiple levels, but let's just for simplicity, let's just consider this a simple one level holomorphic map. And what we can do is we take a copy of the context structure Y here, and we do a next stretching along this contact surface. So the key point is you make sure the point Q stays outside the contact hypersurface Y. And when you do the next stretching, it might break into, for example, it might break like this. The top level, I'm not going to focus on any lower level thing. You have a point constraint here, Q, and you have a point constraint here is gamma 0 square check. Okay, so here it will asymptotic to some real orbits on the boundary Y. But the claim is if we have a breaking like this, there's only one possibility, which is like this. The reason is first notice that for action reasons, you cannot have this guy like have higher energy, and you must have 2 because this curve is completely living inside the symplectization, and this orbit is contractible, but these 2 are not contractible. You have to have 2 to make the homology correct, a homotopy class correct. So if it breaks, this is only possible breaking, and we can compute what's the dimension of this moduli space. So the dimension is 4 minus 2n. And here is the important remark of why we can compute the dimension. So even though we don't know whether the filling has first term class is 0, but we know that for this RP2n-1, the first term class is a torsion. So for any curve inside the symplectization, we can compute the virtual expected dimension only with the knowledge of the asymptotics. We don't need to worry about the relative homology class bounded by the curve. So this is always 4 minus 2n, which is smaller than 0, under our assumption. So this curve actually doesn't exist. So this basically shows that for J sufficiently stretched, everything contained outside the contact hypersurface Y. So it's inside the symplectization. Now we are in good shape because we can lift this curve to the double cover because the symplectization has this double cover, which is the symplectization of S2n-1. And when we lift up, we know that this revolve becomes the shortest revolve on the contact sphere. And this is some point constraint. And we know that every curve here on RP2n-1 will lift two curves upstairs, okay? And so we basically need to count how many curves are there in the symplectization of S2n-1. Okay, and we know that for every point constraint on the circle boundary and every point constraint in the interior, if we fix these two, in the case of the contact sphere, standard contact sphere, there exactly one curve. This corresponding to the fact that the symplectic homology vanishes and it's killed by this revolve. So since we have two ways to lift this point Q and two ways to lift this point gamma 0 to check, there are exactly 4 curves upstairs. So downstairs in the RP2n-1, we have 2 curves. So this concludes the computation for this 2. Okay. And if you look at this, you may think that this is where I use the condition n is bigger than 3, but it's actually not the reason why we need n is bigger or equal to 3. Because if you look at this curve here, it's basically, if you forget about the Hamiltonian here, it's basically a double cover over the trivial cylinder over gamma 0. So if you pick your point constraint away from the image of this revolved gamma 0, there are actually no such curve. Actually, you can run a compactness argument to show that there's no such a curve, even in n is equal to 2 case. Okay. But it's just for convenience, I can just use dimension. Okay. And then we have to worry about whether this gamma 0 to check is a closed class. Unfortunately, it might not be. So the D plus of gamma 0 check may not be 0, but the only possible contribution is to gamma 0 hat. But we don't know. We don't know whether what's the number of it. But for this proposition, it's relatively easy to show. You just need to apply next stretching and consider the action. That's enough. And the last piece is the positive differential acting on gamma 1 check. So we can fix the error created before. So D plus of gamma 1 check is 2 times gamma 0 hat. And this is, in fact, the differential in the Giesen exact sequence because all these gamma 1, gamma 0 are coming from this simple revolve, which a priori is parameterized by RP2n-1.
Zhengyi, there's a question from Mohammed Abouzaid.
Yes.
I just wanted to know again about the signs. Why is it 2 and not 1 minus 1? For the second one, yeah, here.
Yeah.
I didn't quite catch it. So
why? So the reason why it's 2 is because basically because the revolve here is a good revolve. So here he kind of have, they are related by this C2 action preserving the orientation. So you can show that so the curve in RP2n-1 lifts to 2 curves upstairs in the sphere, and these 2 curves will have the same sign. And we know the curve in S, the sphere is the algebraic count is positive 1. So, well, depend on your convention. So they will not cancel, actually.
Okay, but I should imagine it's by reduction to the sphere, by lifting to the sphere.
Yeah, yeah. So in sphere, you have 2 curves, and show they are like, the signs there are the same.
Okay.
And yeah.
Thanks.
Yeah. And if this worries about me, this argument doesn't require it's a Z2. You work with Z3, then you cannot get them cancelled anyway. All right, so yeah, I explained these two pieces. Okay, so the last piece is we have to worry about whether d plus 0 gamma 1 check has some non-trivial contribution to the constant. Okay, so this is actually where n bigger or equal to 3 is really important. Okay, so the proposition is for n is bigger than 3, we have the d plus 0 gamma 1 check q is 0 for sufficiently stretch the almost complex structure. So the argument is again by next stretching, but this proposition actually will fail when n is 2. And the number of this contribution will actually equals to the augmentation to gamma 0, the shortest reorbit. So now we can prove the simplex proposition is just following that we take this class gamma 0 square check minus k over 2 gamma 1 check. And from the previous computation, we know it's closed in the positive cochain. And we can compute what's the contribution in the map d plus 0 paired with q. It's always 2. So this implies 1 plus a is mapped to 0. Sorry, this should be mapped to 0 in the simplex cohomology, not the positive simplex cohomology for some a. And then we can use a positive simplex cohomology with this filter, which is slightly bigger than 2, to estimate the cohomology of the filling. And this is relatively small because this positive simplex cohomology only consider kind of the simple reorbit and the double cover of the simple reorbits. And the simple reorbits are parameterized by RP 2n-1. The double cover are also parameterized by RP 2n-1 before you perturb. So there's a multiple spectral sequence. You can easily argue that this guy has rank at most 4 because the real coefficient cohomology of RP 2n-1 is 2. Okay, and you work a little harder to show that only two of them were mapped to the cohomology of the filling, and then you can conclude the symplectic proposition. And this basically finished the proof. Okay. Any questions? All right. So let me explain what happens for the n equals 2 case. So when n equals 2, let's take the exact filling, which is cotangent bundle of sphere. Then, as I said, the last proposition of this d plus 0 of gamma 1 check is equal to the augmentation to gamma 0. And this augmentation is actually 2. And moreover, you can show that the k in the previous slides is also equal to 2. So the d plus of gamma 0 square check is also 2 times gamma 0 hat by next stretching argument. And then you kind of have all these ingredients. You can compute it. So there are a lot of 2s, and they basically cancel each other, and 1 survives. So it will not cancel the simplex cohomology. And this is actually a small portion of computation which is carried out in the paper of Diago and Lisi. So they compute the simplex cohomology of cotangent bundle of sphere using Gromov-Witten, which is basically here's next stretchings argument to compute the simplex cohomology. And this is exactly the same thing. Okay. And on the other hand, in the n equal to 2 case, we have another filling, which is total space of the degree minus 2 bundle. And in this case, we still have the augmentation is non-trivial. The augmentation here is essentially 1 coming from the fiber disk of this strong filling. And I use t minus 1 to keep track of the intersection of the central divisor. I use it as kind of the Novikov coefficient. And you can also compute what is d plus of gamma 0 check square is again t inverse. So actually the behavior, the k is also equal to the augmentation. So as a consequence, you find a closed class in the positive simplex cochain. And it will go map to a class which is 2 minus t to the minus 2 divided by 2, which is actually now a unit in the quantum cohomology. So this is inside the quantum cohomology. But now it's a unit. So again, I map something to the unit, it will kill the whole group, so the symplectic cohomology will vanish. And this is coincides with the result by Ritter. So he basically computed all these line bundles cohomology. And the last case is we can consider what happens for strong fillings. So for strong fillings, the vanishing property is that we can use positive symplectic cohomology to estimate the cohomology of filling will fail because 1 plus A may not be a unit anymore. That's indeed the case for our natural strong filling O minus 2. And this is also shown by Ritter that in the quantum cohomology, there is an element in the form of 1 plus A, which is a zero divisor. And that element is exactly coming from the image of SH plus. Okay. So this explains all these exception cases. So last, I want to talk about some speculations about this proof. So first, note that the quotient singularity by Z2 is terminal if only if n is bigger than 3. So terminal is a algebraic geometry concept about singularities. And moreover, we can prove the similar symplectic proposition for this more general quotient singularity, quotient by ZK. And the proposition that we have vanishing symplectic cohomology holds if only if n is bigger than k plus 1, which is again the region where the singularity become terminal. Okay, and if we look at the proof, what we actually show is we kind of look at the map from the positive symplectic cohomology restrict to the boundary, connecting map from positive symplectic cohomology to the filling, and then I restrict to a boundary. I consider this composition and understand whether 1 is in the image of this composition. And the good thing about this map is this is something can be phrased without explicit reference to the filling. So if we view SH plus as some kind of linearized non-equivalent contact homology via the construction of Bourgeois and Wanshar, the composition map can also be defined just using augmentations and holomorphic curves inside the symplectization. Okay, so this augmentation may not necessarily coming from a filling. And the phenomena here is actually shows that whenever n is bigger than k plus 1, then 1 inside the image of this map is independent of augmentation. So my SH plus W, so W here is maybe misleading because I'm not using any fillings. I'm just using, say, if I give you an augmentation, I can still define SH plus. And the SH plus is using that positive symplectic cohomology. So the phenomenon here is this map where actually this property of 1 inside the image will become independent of augmentation. But whenever n is smaller than k, this property actually depends on the augmentation. So sometimes you will have 1 in the image, sometimes you don't. But it's not clear that these augmentations are actually coming from fillings.
Sorry, I want to ask again. I don't understand this second point where you say, I mean, I can imagine what you're saying, that the map, so I don't understand how SH plus doesn't depend on the filling. I mean, how do you prove d squared equals 0? Couldn't there be some bubbling involving some holomorphic planes?
I'm not claiming SH plus is independent filling. I'm saying that SH plus can be defined using just the holomorphic curves in the symplectization plus augmentation, which is just some algebraic thing.
Okay, thank you.
From filling. And this map can also be defined using just knowledge of the symplectization plus augmentation.
Yes, that makes sense.
Yes, okay. So I'm saying that here, the proof is kind of saying that it's not about there's no augmentation, it's about part of the information is independent of any augmentation if there exists. And since we have this relation between augmentation and filling, so we can pass to some result about the fillings. Okay. So in light of this, I want to make the following, it's quite speculative conjecture, which is if you have an isolated quotient singularity, which is terminal, then the contact link admits no symplectically spherical or Calabi-Yau fillings. So for this kind of singularity, so one way to build a filling for the singularity, link of singularities, you can resolve the singularity. Of course, if you resolve the singularity, it's never symplectic spherical. And by the definition of terminal, basically, if you resolve the singularity, it's never going to be Calabi-Yau. So if you want to find the counterexamples to the conjecture, you have to work very hard on the construction, I guess. Okay, so this finished the first part of the talk I want to, which is a result of this RP 2n-1. Since I still have, I think, 20 minutes, I will talk about the time permitting part in the abstract, which is about the uniqueness of diffeomorphism. But it's basically based on very similar approach. Okay. So for the diffeomorphism type of fillings, there are a lot of known results for along this direction. So the first result is by Gromov, and then also generalized by Eliashberg and Magdorf, which basically they can completely understand the symplectic filling of standard sphere. So it's always blow-ups of the standard ball. And we have a higher dimensional analog of this, which is proven by Eliashberg, Fleur, and Magdorf, showing that so symplectically a spherical filling of the standard ball, it has unique diffeomorphism type when n is bigger than 3. But we don't know anything about the symplectic properties of the filling. And we know that this standard contact sphere is something called subcritically fillable, because you have a filling which is standard ball, which is a subcritical Weierstein domain. So along this direction, this result was generalized by Wang-Scherfer-Turbo, Bas-Gigas-Zimisch. They show that symplectically spherical filling of simply connected subcritically fillable contact manifold of dimension higher than 5 has unique diffeomorphism type.
Zhengyi, you have a question from Sheel Ganatra.
Yeah. Hi, just a quick question about the previous slide. Apologies if I missed this. Is there a general geometric criterion on the contact manifold for which one in the image of the map from SH plus to cohomology is independent of filling? You pointed out this phenomenon for these singularities. Is there some condition that one can articulate for contact manifold in general?
So one thing you can do is if you restrict the filling, that is, if you assume your filling has a Z grading, then the condition is like you can use the asymptotic dynamic convex condition defined by Oleg Lazarev. So if you have this condition plus you have one filling, one is in the image, then for everything is in the image. So the phenomenon there is you kind of have only one Z augmentation, and the map is kind of independent of. So this map SH plus to this depend on augmentation, but there's only one augmentation, so it's always that map. But the phenomena here is not about there's only one augmentation. It's about some portion where independent of augmentation. But if you restrict your filling a little bit, then there are some cases you can say one is always in the image. Yeah.
Thanks.
All right. Okay. So they have this nice diffeomorphism type for a much wider class of contact manifold. And there are some very nice results. One is by Chris Wendell. He showed the filling of the co-sphere bound of torus, basically unique up to blow-ups. And there are also some other cases for length space. And recently there are 2 proofs of the co-sphere bound of torus by Bowden, Gironilla Marino, and Gagas, Wang, Zimisch. Okay, so a lot of this proof basically use homological informations of the moduli of certain moduli space of holomorphic curves, and what they get is basically some information on homology of the filling, except the proof of Wendell, which he actually used the geometry of the moduli space. So the result actually is much stronger in Wendell's case. Okay, but we can package all this homological information using symplectic cohomology, and it's much more flexible. So the results I want to talk about here is the following. So let V be any Liouville domain Then for any symplectic spherical or Calabi-Yau filling W of Y, which is the boundary of V times D. D is a disk in C. Okay, and then we have the following. The first one is the restriction of cohomology from the filling to the boundary is independent of the filling. In particular, W is always exact. And second is SH is 0. So this is another example of 1 is always inside the image for like any filling, any augmentation. SH plus is independent filling now. And the W is diffeomorphic to the standard filling glued with a homology copolygon from Y to Y. So the main difference of this between this and what Barskager's image proof is here I only assume V is Liouville, so they have to assume V is Weinstein. So this is basically the maximum generality of this type of phenomenon. Okay, and another thing is I'm not assuming anything about like first term class of V or anything else. So in fact, this SH plus is independent filling is different from all previous null results, which is kind of like using next stretching and index argument, because now it's not necessarily Z graded actually. So it's not a prior effect, it's actually a consequence. Okay, and based on them, I can prove the following, which is under the same assumption above. And if you assume pi 1 is a billion, then the interior of the filling is diffeomorphic to the interior of the standard filling, V times D. And if moreover the whitehead group of pi 1 of the boundary is trivial, then the diffeomorphism can be extended to the closure. So you can get a kind of diffeomorphism type result for the filling. Okay, so the proof is actually quite simple. So I'll give you a one-line proof of the theorem. So first we pick a contact form on Y, such that because it's coming from a product, so this is V direction. So we can pick a contact form that all these low periodic orbits are just picking up all these circles circling around the V, around V. And then we can consider the positive symplectic cohomology with only pick up all these rib orbits. So it's positive symplectic cohomology with action smaller than 1, restrict to filling, restrict to boundary. And this map is independent of fillings and augmentation. And then it's actually isomorphic to the kind of standard one. But for standard ones, this thing can be computed relatively easily. The positive symplectic cohomology is just 2 copies of the cohomology of V with degree shift by 1 and by 2. So these are all generated by check. These are all generated by hat. And from this standard filling, I know this map will hit 1 because the symplectic cohomology of the ambient V times C is 0 by the work of Wangshar. But in fact, you know that this scaling happens at the very early stage when you can include all these simple orbits. Okay, and then the fact is we know that if this map is independent of filling, and we also know all these hat orbits will necessarily map to 0 in the cohomology of filling. So we only need to care about what is this check part to the filling and to the boundary. Now for the standard one, we know it's an injective map because it's V times C. And from the proposition of vanishing that I know that this map from the positive symplectic cohomology to the cohomology filling, this guy is surjective. So you have a map which is composition to injective map, but this map is surjective. So here you have isomorphism. So you can kind of recover the cohomology of filling, you can recover the restriction map and everything. And the remaining of the argument is kind of the more standard cobolism argument used in first used in Ashberg, Fleur, Mekdorf, and then Barskager's image. And the pi 1 a billion cases, you can basically consider a universal cover of this guy and to argue that the homology cobolism is actually a H cobolism. And then you can get a diffeomorphism type from there. Okay. And I think I have finished all my materials, so that's it.
Okay, are there any questions for Zhengyi? So something that I wanted to ask is, can you say what the number theoretic conditions on n and k are so that your technique applies to s2n-1 mod zk?
It's kind of related to the how you write out. So I didn't prove for every k. So I only prove k is prime number, and the condition is related to how you write out n as a p-adic number. And the conditions basically require the p-adic representation of n has kind of enough non-zero positions. So the n equals 2k, you can think of it as writing it as if you write n as 2-adic number, you only have one non-zero digit. So that's too bad. But if you have more, then it's good. But I don't think this condition is necessary. It's just, I don't know how to argue a contradiction just from the cohomology of filling is small to the, to there is no such filling. Yeah.
Thanks. Okay, any other questions for Zhengyi?
Yes.
Yeah,
yeah, so you had repeatedly this condition about either something is Calabi-Yau or something is, or it's symplectically aspherical. Can you change all of those to something like the non-existence of zero divisors in quantum cohomology?
Yeah.
Including this last one about the diffeomorphism?
Include last one. So you can, the last one, you can say like exclude certain holomorphic curve in certain degrees, then it's done. Then it's also true. And the Calabi-Yau is slightly different because if you have Z grading, then if you show something mapped to 1, you don't have to worry about all the remaining term because all the remaining term has different grading. And 1 is always unit in the quantum cohomology. So Calabi-Yau is slightly different. But the vanishing will hold if you assume Calabi-Yau.
Thanks.
Yeah, and a remark for the last proof is it's a one-line proof, but it's not actually proof because many things. For example, you don't have C1 and 0, so there are a lot of complications.
Any other questions for Zhengyi?
Yeah, so they can actually get something for the V times C case. So you can again run their argument. What they prove is the cohomology from the any filling. Sorry, they use homology. The homology from the boundary into the filling is always surjective. That's all they can prove. The reason is they basically only use the holomorphic curve, kill the symplectic homology. They only use that curve. And then they need to play with the duality to squeeze more homological information from that. So they kind of need to argue that the homology of V is not too big. So they have to assume V is Weinstein to get the maximum result. But in general, they can only get weaker result.
Anyone else? Okay, then let's thank Zhengyi again.